Welcome back. Today we are going to apply linear equations. So we've been solving linear equations, now we're going to apply them to quote-unquote real-life situations. So that means, unfortunately for you guys, it means word problems, all near and dear to your hearts. So in solving word problems, we want to come up with a plan for solving them. Okay, so what you want to do with your problem solving plan is you want to first read the problem. Okay, so you want to read that problem. Okay, and read slowly. You might have to read it a few times. But don't try and answer the question. That's one of the common mistakes is you try and read the problem, you want to go right to the answer. Doesn't work very well. Read the problem slowly, determine an unknown, and again, don't try and answer the question. If there's a geometry problem, it mentions a triangle or a rectangle or a square or increasing a lot size or something like that, draw the diagram, okay, especially for geometry, picture frame type problems. Draw a picture, draw a diagram, see how that's going to help you with what's going on, okay? What you want to do then is after you read the problem, you determine your unknown, assign a variable to the unknown. So be real clear. So X is the number of widgets. W is the width of the rectangle. Okay. Y is the amount of solution added. That kind of thing. Tell me exactly what the variable is. Okay. Then, based on the information on the problem or your diagram or even a table, we're going to do some tables, write an equation using that variable. Okay. Then solve the equation. Let algebra do the work for you. And then finally, once you solve the equation, once you find out what X is or Y is or W is, whatever it is, once you've solved it, make sure you answer the question. X, whatever you come up with, X is not always the answer. So make sure you answer the question. And then look at your question. Does that solution make sense? So let's go ahead and do some sample problems. So for each problem, you want to identify your variable, write an algebraic equation that represents the scenario, solve the equation to answer the question, and you might have to draw a diagram. So we're going to start here right off the bat. The length of a rectangle is 1 centimeter more than twice the width. The perimeter is 110. Find the length and width of the rectangle. So for some reason, that whole word problem isn't listed in there. But that's what we want. We want to find the length and width of the rectangle. So we're going to start by drawing our rectangle. So we've got a rectangle. Okay. We want to find the length and width. The length is 1 centimeter more than twice the width. So twice the width would be something like 2W, and 1 centimeter more is 1. So this side must be the width. So finishing off my rectangle, W and 2W plus 1. So my lengths are the same, my widths are the same. The perimeter is 110. We know that we can add up all the sides, or 2 times the length plus 2 times the width. So 2 times the length, 2 times 2W plus 1 plus 2W equals 110. I'll go ahead and distribute the 2. So we get, look at that, we get 4W plus 2 plus 2W equals 110. So that would be 6W plus 2 equals 110. Subtract 2 from both sides. 6W equals 108. Divide by 6. And W equals 108 divided by 6. Maybe we'll do a little long division on the side here. We don't have a calculator handy. So 6 goes into 10 one time with a remainder of 4. So 6 goes into 48 8 times. So we get W is 18. So once we know our width is 18, we know that our length is 1 more than 2 times that. So our length 2 times 18 plus 1 is 37. So our rectangle is 18 by 37. And we've answered the question. Problem number 2. In 2011, Milwaukee Brewers pitchers Gallardo and Greinke combined for a total of 555 strikeouts. Greinke had 25 more strikeouts than Gallardo. How many strikeouts did each pitcher have? Okay. Greinke had 25 more than Gallardo. So let's let X equal the number of strikeouts for Gallardo. So that must mean if Greinke had 25 more than Gallardo, that must mean X plus 25. That would be Greinke's strikeouts, wouldn't it? Okay, so X is Gallardo's. Well, we know that Gallardo's plus Greinke's equals 555. So X, Gallardo's strikeouts, plus Greinke's strikeouts, X plus 25, equals 555 total strikeouts. Well, that's 2x plus 25 equals 555. I'm going to subtract 25. So 2x equals 530. Divide by 2, because we want to solve for X, Gallardo's strikeouts. X equals 265. So apparently Gallardo had 265 strikeouts. So that's Gallardo. Good job, Giovanni. And Greinke had 25 more, which would be 280 strikeouts for Greinke. Not too bad. All right. Moving on. In 2002, there were 301 long-distance area codes in the United States, an increase of 250% over the number of area codes in 1947. How many area codes were there in 1947? Okay, so our question is, how many area codes were there in 1947? Well, let's let X equal the number of area codes in 47. Okay. Let's go back and read again. There were 301 long-distance area codes in 2002. That was an increase of 250% over the number of area codes in 1947. 250%, that would be 2.5 as a decimal, right? 250 over 100 is 2.5. Okay. An increase of 250%, well, that would be 2.5x. So our equation becomes our area codes in 47 plus the increase. So the number in 47 plus the increase equals the total of 301. So the number 47 is X, plus the increase in area codes, the 250% is 2.5x, equals 301 total area codes. Well, 2.5x plus x is 3.5x equals 301. I'm going to make that 7/2 x equals 301. And now I'm going to multiply both sides by the reciprocal of 7/2, or 2/7. So you get x equals 301 times 2/7. So I'm going to move my work over here to the further to the right. So now 301 times 2 over 7 equals x. That's 602 divided by 7 equals x. Doing a little bit of long division here, we get 86 equals x. So there were 86 area codes in